In this second part we will point at some of the limitations of the application of the relative permeability curves to multiphase displacement modeling. Basically, we will try to identify those scenarios in which Darcy's law does not apply to multiphase flow, and that will allow us to differentiate between mathematical model and physical reality. In other words, we are going to see what happens when everything fits into an equation that does not link the data of interest. To summarize what we discussed in the first presentation, we are going to use an image that allows us to compare different displacement scenarios. Some of the equations that were analyzed in that first presentation. And a phrase that summarizes many of the characteristics and problems that generates the use of relative permeabilities. In this second presentation we are going to make a critical analysis of the concepts already presented and we will add some new others. This will allow us to identify the origin of some recurring problems in reservoir modeling. It was not explicitly stated when we looked at this image, but it is important to note that in the different scenarios, the variables that are linked are the production rates on the outlet face, the face of the model we are analyzing, and the average saturation of the system. During the analysis, saturation status was not measured nor considered on the production end. So, it is valid to ask whether we are making the right evaluation by taking a variable that is determined only at a point in the sample, in fact, on one face of the sample, and then relating it to the whole system average saturation. Well, the answer is not straightforward and is linked to the fundamentals of the theory developed to adapt Darcy's law to multiphase flow and reservoir modeling needs. When we presented Darcy's law for linear media, we mentioned that it is a remarkably simple law, linking the variables that describe single-phase flow in porous media. This law allows to define permeability in an operational way. In everyday language, when we define permeability without equations but using words, we usually use expressions like is the ability of a porous medium to conduct, transport, drive, transfer or mobilize fluids. But we never define it spontaneously as the ability to produce fluids of a certain porous medium, despite the fact that those of us who work in reservoir engineering try to predict the production of fluids, as the basis for the economic sustainability of any commercial exploitation. Basically, when Darcy carried out his experiments, he used a different device than the one we see in this image but involving the same concepts. Darcy used, as in this image, a porous medium 100% saturated with water. In fact, they were sand filters dedicated to purifying waste waters. During his experiments, the water injection flow rate was the same as the production flow rate and, therefore, talking about conducting, producing, or injecting fluids implies the same numerical value when working under the conditions in which this law was born. The numerical values are identical when talking about water injection or water production rates, and the same value defines the transmission rate because there is no way of driving something different from what is being mobilized at the ends of the system. This concept is applicable to all incompressible single-phase flow. In these cases, we speak of a flow rate value, without indicating where along the sample the measurement is made, because it is not necessary to do so. But, what is the situation in the case of multiphase flow? Now we will introduce a new term. In multiphase flow we define the effective permeability of the system to any of the circulating phases. So when we write Darcy's law to describe the flow of a particular phase, for example water, we are interested in the flow rate of this phase linked to the pressure difference applied to it and the viscosity of this fluid. The geometric factor does not depend on the fluids and so, the permeability of the porous medium must be corrected by a factor that takes the form of a relative permeability curve. We do the same operation in the case of oil. In this way, we call the product of absolute permeability times relative permeability as effective water permeability or simply water permeability. Once again, we do the same for oil. Both values depend, of course, on water saturation. Unlike absolute permeability, which is a unique value for the sample, Effective permeability is a value that depends on the saturation of fluids in the system. In summary, what we are doing when defining the concept of effective permeability is maintaining Darcy's law form, but using customized variables for each phase. It should be noted that effective permeabilities are always lower than absolute permeability, since the presence of a second phase always hinders the flow of the other. Operationally, to determine the effective permeability of a phase, its flow rate must be measured at a certain saturation and compared with the flow rate obtained when that same phase is 100% saturating the porous medium. The previous analysis allows us to deepen the concept of relative permeability. We have already mentioned that the flow rate of any phase under multiphase flow conditions, for a given water saturation, is determined by the variables shown in this equation. And we have already mentioned that the definition of effective permeability corresponds to the product of absolute permeability times the relative permeability to that phase. This allows us to obtain the relative permeability of each phase as the ratio between the effective permeability and absolute permeability of the system. Since absolute permeability is a constant, obtaining a rel-perm curve as a function of water saturation implies having the ability to determine effective water permeabilities for the entire range of water saturations. What follows is an observation that seems trivial, but in order to determine this we need to physically have a value for the flow rate of the phases we are analyzing during the displacement. And this is not so obvious as it may sound. What we have done so far is just a mathematical manipulation of Darcy's equation, and what we will do next is a physical interpretation of the phenomenon. To understand what we have said, let's see how we could calculate effective permeabilities in an example that we have already seen. In the case of effective water permeability, what we have to determine is the flow rate of water that circulates through the system, since the other variables, in principle, are very easy to determine. The geometry remains constant, we set the pressure difference, and the viscosity of the water remains constant during the experiment. Therefore, measuring the effective permeability to water in a displacement involves measuring the water flow rate during that same displacement. For a given water saturation, we will identify this expression as equation 1 because we are going to mention it later. If we take the case of a sample like the one we have already showed and we inject water into it, water displaces oil in such a way that, at the moment represented in this image, the sample is producing only oil while there is only water being injected through the inlet face. And the water saturation in the sample is about 50%. To run some numbers in this example, we can imagine that we are injecting a typical laboratory flow rate, 1 milliliter per minute of water. And we are producing, well, we are not producing water at the moment. So we have a little problem to apply equation 1. At the moment chosen for the calculation, the values of the pressure difference, the viscosity, and the geometric factor are perfectly defined, but for the water rate, we have at least two options. So, which value should we use in equation 1 to calculate the water permeability? The water injection rate, the water production rate, or perhaps a mathematical average? Well, maybe the problem is not very clear at this point, so let's see an example that takes us a bit away from reservoir engineering. Let's imagine that what we are seeing is a two-colored ball. For this first analysis, we are going to simplify the natural world to just two colors, in this case, blue and yellow. If someone asks, what color is this ball? We could answer, in line with the previous example, that the ball is blue, or it is yellow, or it is green. And clearly none of the answers is correct. None of the three answers exactly defines the object we are studying or trying to model. Well, oddly enough, the way that relative permeability curves are commonly used is equivalent to saying this ball is green. But the general problem is much more complex. The general problem is not equivalent to modeling a two-color ball, but rather a multicolored picture in which, again, it is impossible to define what is the color of the image. In the case of the ball, we could somehow manage to describe it with two colors, but, Defining the color of this image is impossible, no longer physical but even grammatical. However, each pixel on the screen has a perfectly defined color. The same happens in a non-stationary multiphase displacement. What we are looking at this moment is a transparent, laboratory cell where blue water is being displaced using air injection. At the time this photograph was taken, the system has a saturation gradation equivalent to the color gradation that we see in the image above. Again, in this case, the system, as a whole, does not have a defined water conduction capacity, but it does have a distinct water conduction capacity at every point, depending on the water saturation at that particular point, and how this water saturation was reached. But, then, if real systems are so complex, how comes that the relative permeability curve that require a defined water conduction value is measured? Well, recreating the original conditions. This means that injection, transmission, and production must be interchangeable verbs or, what is the same, generate unique flow rates. In real porous media there are only two solutions to this requirement. The first solution consists in working in a steady state, where the injection flow rates of all phases are identical to the production flow rates. In a laboratory test, a sample like the one we have already looked at is taken and, not only water is injected, but water and oil are injected until the same ratio of water and oil that is being injected is produced at the outlet end. Under these conditions, what is injected and what is produced are the same, and therefore that value defines what is driven inside the sample. The second solution can be obtained at any point of a non-stationary displacement, as in the case analyzed in the previous image. In summary, there is no possible solution for a system in transient state, either a laboratory plug, a numerical simulation cell, or a hydrocarbon reservoir. Not that it is difficult to define. No, there is no global fluid conduction capacity in any of these systems, and therefore, there is no chance of permeability calculations, leading to no effective permeability and no relative permeability value. In fact, in a real displacement, when we take a finite block, of whatever size, a cubic centimeter, a cubic meter, or of a cubic kilometer, when we assign to it a certain average water saturation, each point of that system, each plane, each face, or each well, located in that block or cell, has its own capacity to transport fluids. So, there is no defined a unique capacity to transport fluids. And this brings us to a summary of this talk. While reservoir modeling requires curves that quantify the production rates of different phases, for each average saturation value, in systems that are three-dimensional, highly heterogeneous, and subjected to variable equilibria of the capillary and gravitational forces, both in time and spatial location. The solution regularly used for modeling takes the form of relative permeability curves, which quantify the relative transmission capacity, not production, of the different phases, for each point saturation of fluids, and are obtained in linear and homogeneous porous media, under exclusive domain of viscous forces. Adding the already mentioned Laurie Dake's phrase where he shows that it is assumed that these rel-perm curves are intrinsically correct, and all the theory and practice are assembled to accommodate this generalized point of view, we can see the magnitude of the modeling problem. Regularly used curves do not model the variables of interest and, possibly worse, they describe the ability to transport fluids in the reservoir, instead of the ability to take or produce those fluids on the surface. Well, the whole scenario to analyze is much broader. In fact, in the following talks we will discuss several topics related to what was presented in these two brief introductory talks. Next topics range from a detailed analysis of the limitations of the frontal advance theory, a discussion of endpoint saturations, irreducible water, residual oil, critical gas saturation. We will also discuss what is accepted as an operational solution to deal with the mentioned inconsistencies, based on what is known as implicit calculation or on the definition of relative permeability pseudo-functions. And we will also discuss how reservoirs could be modeled using rel-perm curves in a different fashion. These are just some of the topics of the next talks that we will develop in these presentations.